Good morning, everybody. Let's get started. It's my big pleasure to welcome you all in this track. We have a number of fascinating talks, and let me get started with the first one right away. Let me introduce the first speaker of today. He is a person who carries many titles. One title, you could call him Mr. SCION. You could also call him Mr. Please Fix the Internet. There's a bunch of things that you can tell what Adrian Perrig is doing. He came to Switzerland in 2013 from Carnegie Mellon University, and he had a very clear mission, a very clear focus, saying, I want to revolutionize, I want to change the internet, because what we have today in the internet is not acceptable. This is a state that we cannot really afford in terms of resilience and in the focus of a mad world. And Adrian had this very clear picture, and he was criticized sometimes because people said, this is way too narrow, way too focused. And now it turns out it was not too narrow. It was just the right decision to put all cards in this direction, because now, 10 years later, SCION is very successful. So please give a warm applause to Professor Adrian Perrig.
Great. Yeah, wonderful. Thanks so much, Raphael, for the nice introduction. So nice to be here. And yeah, actually, the trying to fix the internet goes back a long way. Back in 1991, I already worked with Cisco routers for a company, putting them together, already thinking about some security aspects back then. And since my beginning of my PhD in 97, I worked essentially on securing internet protocols. And as Raphael was saying, after some time at Carnegie Mellon, we decided to work on a new internet architecture, and which then became SCION. And so I'm happy to be here today and show you about all the things that have already happened, and also ask you for your support for the next steps moving forward. So with that, I'd like to start out by introducing how SCION works in one slide, just to give you some background, technical background, how this works. And on the slide, we see the small circles represent autonomous systems. That's a technical term to indicate an ISP, like a Swisscom or a Sunrise, a Cyberlink. Here in Switzerland, or also an entity like Switch or ETH Zurich would be one of these smaller circles. And like in today's internet, they are connected to each other. And what SCION introduces are isolation domains. These are these colorful ellipsoids that groups these autonomous systems together. And essentially, SCION then is a path-based architecture where, and this is a little bit technical, my apologies for this, but essentially any routing protocol has a control plane and also needs then a data plane. So the control plane finds paths, how to get from point A to point B. And what's different in SCION is, compared to most other architectures, is that SCION is a path-based architecture. So in this example here, we have a node F who wants to communicate with a destination in S, in this autonomous system S. So for instance, this could be Princeton University in the US, and F could be ETH Zurich. And so we learn, in this example, these colorful path segments that the architecture creates and disseminates. And then when my computer wants to send a packet, knowing these path segments, then it uses the data plane to send the packet. And here in this example, we have two different choices how to get from ETH to Princeton University, and essentially through two different combinations of these path segments. So then the end application actually takes these paths and puts them into the packet header. And these are also optimized, so they're very small and also contain cryptographic information to avoid entities to change this information. And so then the packet either goes on this upper path or on this lower path from source to destination. And so this looks very simple, right? So it's a very simple architecture, but it's actually very powerful to have these concepts. And these very simple concepts, even at this level, the routers actually become simpler, because the routers, they don't need inter-domain forwarding tables anymore. And the routers can, for the most part, operate in a stateless fashion to simply follow these instructions for the inter-domain connectivity. But actually, these very simple approaches have several additional benefits. So one is also path transparency. So that means when you send the packet, you already know which path this packet is going to take. And this is already very useful, but it also enables an additional property called geofencing. So that means you can restrict your packets to a certain geographic area. And that, for a lot of compliance applications, this can be very, very important. It also enables multipath. That means that simultaneously you can use all the paths that you have available at the same time. So you can send one packet on one path, another packet on another path. And today's internet is essentially single path. So today's internet will pick one path for your packets. And as a sender, you don't have much choice over which path this packet is going to pick. Again, multipath seems like a natural concept, but it's also extremely powerful. It helps a lot with resilience and achieving high reliability in the face of network outages and so on and so forth. So this brings me also to the next point, is failure resilience, rapid failover, because all the paths can be used simultaneously and there's no state in the network. Your application can fail over within milliseconds or microseconds even, or even duplicate a packet and send it twice on two paths and so on and so forth. So all these methods, mechanisms dramatically enhance resilience compared to today's networks. SCION also has a lot of built-in mechanisms to prevent routing attacks. I won't have the time to cover them, but there's different cryptographic methods built in to protect the creation of these path segments and the dissemination of these path segments, as well as then different high-speed crypto to also verify the information in the packet header during forwarding. Sovereignty is another property of SCION that has gained a lot of relevance recently, because each isolation domain locally defines the cryptographic keys. There's no more global cryptographic keys that need to be trusted. So this is another, we believe, a big deal. So you can use SCION to build sovereign networks, yet connect globally to everyone else in the world. Right? So it's another, we believe, game changer, because there's no other system, as far as we know, that can be both in an open network, yet define local keys that govern the local operations. So SCION has been very valuable in environments that require highly reliable connectivity. And so the SSFN was born and selected SCION as a way to communicate, the Secure Swiss Finance Network. And this has been a very long project, and thanks to this project, perhaps I'm even standing here, because SCION became successful and became used thanks to the Swiss banking ecosystem selecting SCION as the way between the banks to communicate. And what's exciting is that the previous network has been turned off in the meantime. So all the Swiss transaction processing, the Swiss interbank clearing, is today going over a SCION network among 321 banking participants, also insurers and many other companies that participate. So based on this model, and SSFN worked really well and lowered the cost also for banks to establish connectivity, other infrastructures followed with the Secure Swiss Healthcare Network, SSHN, that enables 50,000 doctors today in various doctors' offices in Switzerland to now use SCION to communicate with their healthcare IT provider. And also recently, this Secure Swiss Utility Network was born, the SCION, for electric companies and other infrastructure like water and so on to communicate with each other. And the most recent addition is the SEPN network, the EFT POS network, that will also carry all the transactions we do over a SCION backbone initially, but then also expanding to enable SCION connectivity between all the different entities in the payment ecosystem. So there's today over 20 network service providers that provide SCION connectivity. So it's really the case. You can go and order a SCION internet connection today from them. And that's obviously really exciting. So all these use cases, though, they rely on a translation from IP to SCION and back to from IP to SCION back to IP, the SCION IP gateway. And essentially, none of these applications are aware that SCION even exists, right? So it's all these leveraging this translation, so none of the applications was updated. But a lot of the benefits of SCION come when the application is aware that SCION exists and is able to optimize even between IPv4, IPv6, and all the different SCION paths to see what is now the best way to communicate. And so with this, we see that IPv6 actually has helped SCION a lot. So we, thanks to Jelte van Bommel in our group, he drew this diagram. So IPv4 is all comfortable, right? Everyone is using IPv4. And IPv6 had a lot of work to do already to get to the level of adoption we have today. It took over 20 years. But because IPv6 is another system and requires switching between IPv4 and IPv6, IPv6 is greatly helping SCION and native SCION connectivity through systems like Quick, Multipath, and also Happy Eyeballs that perform. These are libraries for communication, or also Happy Eyeballs to switch between IPv4 and IPv6. These systems greatly facilitate now for SCION to be used without requiring 20 years of adoption, right? Because the system is already in place to switch between IPv4 and IPv6. Now SCION as a third option is a relatively minor change to be added, and all the applications using these libraries can then natively use SCION. So let me dive a little bit deeper into this matter. But first, now to come back, essentially if you have an application, you can of course use one of the existing SCION libraries in typically a small number of changes to the application to now make the application SCION aware. And this is great, right? So in some cases it just requires a couple of lines and your application can send native SCION packets. But the problem is, there's millions of applications, and it's unrealistic to believe that all these authors are going to build in SCION. So instead, the way IPv6 paved the way is through, again, this library called Happy Eyeballs that is today built into pretty much all the browsers and also many programming languages directly, like in Go. It's also directly built in. And Happy Eyeballs was created to reduce the complexity of switching between IPv4 and IPv6. You may think that's easy to do, but actually in practice, there's a lot of failure cases that can occur that gave birth to this library that especially Apple was pushing, and so enabling application programmers not having to worry if they need to use IPv4, IPv6, or even switch between them while the connection is ongoing. And also measuring which one's better, and so on and so forth. So this library is now in place. As I mentioned, all of you are using this every time you open a web page. This is invoked. Now, given that this exists, SCION essentially can be added as a third option to also provide optimization opportunities over all the different SCION paths that are available. And so, of course, if IPv4, IPv6 is faster, by all means, that should be used. But you can already imagine when you have multiple choices, you can now optimize your connectivity and use one of the SCION paths instead if one of those paths has some property you would like to achieve. Similarly, Quick Multipath also is a similar library that now becomes is able to simultaneously use IPv4 and IPv6, and that's another great example how SCION can actually be added to systems without updating the applications. So in the IETF, we have been active, and when I say we, it's the royal we. I'm not too much involved there. It's the part of it is my research group at ETH, but for the most part, it's a SCION association or also other research groups that are pushing these different drafts in different working groups. So first of all, Multipath Quick. It's actually the regular Quick that is becoming Multipath. So all of you are using the Quick system on a daily basis. The majority of web connections are over Quick, and Quick essentially is replacing TCP. And so it's a great opportunity now that QUIC is moving towards a multipath implementation, which all of you again will use as soon as this becomes standardized and is being pushed into all the endpoints. It's a great opportunity for also adding SCION, because if you're in a SCION-enabled network and SCION gives you lower latency or better properties, why not use it, right? It's like when you come to ETH, anyone on the ETH network can use SCION natively, and we're expanding this to other places around the world. When SCION is available, why not use it? And so from Tony John from OFGU in Magdeburg, it's a university near Berlin, they essentially are pushing a system for multipath transport protocol with deadlines, DMTP, and they have drafts that push that, also as part of using SCION, of course, for the connectivity. And in our group, Tilman Zashke is also submitted a first draft as well to gain traction there to get into these standardization efforts. Also in the Happy Eyeballs, there's now an openness of the working groups to open up to other internet architectures. And so this is very welcome for us to also come with SCION to add SCION as a third or other internet architectures as fourth or fifth options and so on. And so this is, I hope you agree with me that these are real game changers, because once these systems are in, right, tens of thousands of applications can then send native SCION packets if, of course, the destination server is also SCION-enabled and you're in a SCION-enabled network. There's two very big ifs, but nevertheless, these are really exciting opportunities. So to further bring, I'm just looking at the time, make sure I don't speak too long. As a professor, we always speak too long. So to be careful, I keep my time. So we've been building a global native SCION network to enable many people to be covered and being able to use native SCION connectivity. And so we have been pushing a project called Sierra that is just the regular SCION network, but extending it to different universities across the world. So you see we're on 5 continents. There's an Australian university now also joining, and several additional universities in the US also coming online. As Internet 2 is offering a SCION VLAN, it's becoming easier and easier for universities to join this. And so this is covering roughly 250,000 people across the world. So when you're at University of Korea, for instance, and you're on the EduRoam system there, you will just have native SCION available. So if you have a SCION-enabled Happy Eyeballs or QUIC library, it can automatically pick that up and start using. And so this is what we've built over the last 2 years, this infrastructure. And what was really exciting is also the measurements results, looking at how this network performs, because this is a non-overlay native SCION network essentially, right? So there's no BGP being used when you send a packet here from, say, from ETH Zurich to Korea University. There's no reliance on BGP anywhere on this path. So we then did around 265 million ping measurements on IPv4, IPv6, and SCION to compare the performance of SCION versus IP. So essentially on the x-axis you see a given latency for the round trip time, and the y-axis shows what fraction of ping measurements were below this latency. So essentially at the end you have 100% because all the packets will be below the maximum latency that was observed. And so essentially the higher the curve is, the better it is, right? So if you would immediately go up to 100%, it would mean all your packets globally would take less than 50 milliseconds. So higher is better. So what you can see is that IP is better locally, because the SCION routers are not as highly optimized, I guess, as internet routers. But one thing you can also then see is after a certain distance, roughly at 130 milliseconds, for the average packet, SCION becomes higher performance than IP. For instance, at the 50% mark, SCION is roughly 7%, has a 7% lower median latency than IP. It's even more extreme at the 90th percentile because of this multipath that I was telling you at the beginning. If you have a lot of different paths available, there's a high likelihood that your best path is very good. Right? So you see this reflected here, that the fastest SCION path can beat the internet path actually by quite a lot, especially if you go far. So this was really exciting. Another really exciting result was to see how many paths exist. And this diagram demonstrates from a given source AS to a given destination AS how many different paths were observed. It's not a symmetric graph because it's a routing protocol that picks what it believes are the best paths. So you don't always see exactly the same paths in both directions, even though all the paths can be used bidirectionally. But what's really exciting is that for the most part, you have dozens of different path options. Right? So for instance, from this Korea University I just happened to know, we just redid those measurements. We have 80 different paths to ETH last time we did these measurements. What's exciting is when you have 80 paths, right, you can now imagine how much you can optimize. Right? If you have an application that requires low latency, or you have an application that requires high bandwidth, or an application that requires low jitter or low loss, you actually are starting to use different paths to be optimal for that application. And having a large number of paths enables you to do this kind of optimizations. So now the talk also is about technical specifications and standardization. So I guess all of you agree that it's important to specify and standardize technologies because of the enabling an open ecosystem, but also interoperability as well as gather community feedback. So I think I can pretty much skip this because it should be self-evident. And so the SCION Association is pushing the specification and standardization efforts of SCION, and also together with the members of the SCION Association. So you can see more about and learn more about the SCION Association at scion.org. And essentially, the SCION Association is building a community that to raise awareness of SCION and also build up the community to collaborate, but also pushing specifications as well as maintaining the open source stack for SCION. So the role of the SCION Association is through a technical committee with a number of people from industry and academia to help push these different specifications. And the core SCION specification, I'll talk more about it on the next slide, in aggregate is 224 pages, so far had 10 revisions, and was spending 1.5 years so far at the independent stream of the IETF. I'll explain this a bit more on this slide. So essentially, the goal is to create these drafts and going through this independent stream to obtain RFCs to then start a standardization effort at the IETF once the first specifications have gone through. And so you have the three drafts, the SCION public key infrastructure draft, also the control plane draft and the data plane draft, that together have these 224 pages. And so this is now nicely moving along, this independent stream. And so hopefully this will soon conclude in RFCs for these documents, which then enables us the formation of a working group at the IETF and facilitates the creation of the working group as well as starting the standardization effort for all these, for the SCION system, enabling the whole community to collaborate and participate. You can download all these documents at this datatracker.ietf.org URL. So over the last years, the ambition grew a lot for SCION. And so we see it as a core connectivity technology operating side by side with IPv4 and IPv6. We don't see it as to replace IP or to replace BGP, but really enable an additional option for applications that require high availability and or the properties that we've seen so far. And so we see that if SCION is added to these libraries, that hundreds of millions of devices would then start supporting SCION. In some cases, even over 1 billion devices will support native SCION connectivity. And given the progress in discussions with different entities in this space, we're optimistic that we can reach this goal of being included in some of these libraries within 3 to 5 years, and then covering hundreds of millions of users worldwide that have native SCION software that will then start sending SCION packets as soon as they're in a SCION-enabled network. Again, one if is they have to be in a SCION-enabled network. The second if is they have to communicate with a server that also is SCION-enabled. And again, to reach this goal, we need to drive the specifications and also facilitate the broad availability of native SCION connectivity, which is not so simple, but we're making also good progress here with the 250,000 people you've seen in this Sierra network I was showing earlier, but also we're expanding that to now 1 million users, and we're confident in the coming months that this network will actually cover 1 million global users. And so we're working on extending these quick and happy eyeball libraries that then creates the opportunity to natively send SCION traffic. But this is also a call for help. Obviously, it is not easy to achieve this, and I'm hoping all of you can also help us and support us in reaching this goal. We can only reach this as a community, but the payoff is that all our applications will have the ability for highly available and secure connectivity on our global networks, and really realize this vision of a globally secure internet that is easily available and usable by anyone. All right. So with that, thanks so much for listening. And
many thanks, Adrian. So we do have a couple of minutes for questions, and I encourage you to raise your hand because we have a microphone that is coming. And until people are prepared, let me start with the first question, Adrian. People often believe security and cryptography is expensive. You know, usually when you build these into the systems will suffer in terms of efficiency. For SCION, the opposite is the case. The system is more secure, and it's even more efficient or faster in the data plane. Can you explain in 2 sentences how this could be achieved?
Right. So of course, if you would remove the cryptography in SCION, it would get even faster. But based on a different design, it turns out the routing update the route table lookup can be expensive when you have large-scale routing tables. And it turns out that the cryptography, in terms of energy that is required, and also in terms of number of transistors, etc., actually requires less effort than the route table lookup. Right? So that's one of the indications. Right.
So even the ecological footprint will be improved. That's great.
That's a longer discussion to claim that. But I'm happy to have that discussion with anyone. We can put 100 francs on the table, and then after 1 hour discussion, we see who gets the 100 francs. I'm not confident, but I'm optimistic I can win a lot of these discussions, because we've had almost a decade also work in this space, looking at, and there are some surprising ways SCION can actually help and lower the CO2 footprint. But it's not an easy argument I can make here in 1 minute.
Excellent, in times of AI. Great, so we have a question in the first row.
Mm-hmm. Yes, great. Thanks, Adrian. I know nothing about this routing stuff, so my question might be silly, but as an attacker, you get now, instead of 1 path, 100 paths. Can I more effectively create DDoSes by multiplying my traffic by 100 at 0 cost?
Yeah, very good question. So one way, things are never black or white, right? Things are always somewhere in between. And SCION definitely enables the attacker to also pick the path. But now imagine the attacker has to control all the paths or close all the paths. As long as one single path exists that is available, the legitimate user can still reach a server. But also SCION then has additional mechanisms built in, like one system is called hidden path, where you need a cryptographic key to use a path. And use a link. If you don't have the key, you cannot send a packet. And that's very powerful. But then also next year, if everything goes well, we'll have Hummingbird. We had a system called Colibri, and now it's called Hummingbird. That enables global quality of service that then gives you guarantees for connectivity if you manage to get all the reservations. And so then with that, you get very strong guarantees for connectivity, even on a public internet. So it's then very powerful. Right?
Wonderful. We have time for one more question. Yes.
Short question. Does it make sense to use SCION on IoT devices?
Absolutely, right. We just are releasing a new stack that's written in C exactly for IoT devices. It's a high quality C implementation specifically written for small IoT devices. And it's open source. It's our research group at ETH that's doing this.
Great. Adrian, before we let you go out of the room, can you say in one sentence, if people want to experiment with SCION, what is your recommendation? What is the thing they should be doing tonight in order to play around with SCION?
Call your ISP. But actually, jokes aside, there is a new system that's going to launch next year where you can get native SCION connectivity from anywhere in the world through a system called SNAP, SCION Network Attachment Point, where then there's a quick connection going to that, and then from anywhere in the world, you can, any device, be it a Mac or a Windows machine or whatever, you can obtain SCION connectivity and send SCION packets. So this is one way.
Thanks, Adrian. So please give a warm applause to Adrian. Thank you so much.
Thank you. It's okay.